All right. So welcome
Okay.
to part two of Mingzhi Yang's talk on quantum Schubert calculus for smooth Schubert divisors in FLN.
Yeah, I will introduce a presentation of the quantum cohomology ring discovered by Peterson Ness. Let Y be the closed subvariety in G mod B defined by this simple reflection. So an element GB lies in the Peterson variety if and only if the conjugate of the principal nilpotent element of F under the action of G has this pattern. So some it vanishes in some entries. And then we consider the intersection of Peterson variety with an opposite Broussard cell associated to a parabolic and denoted by Y up lower P. And then we consider an open part of Yp by intersecting the biggest supercell, and we get Yp circ. And then the Peterson isomorphism theorem says that the quantum cohomology ring of the flat variety G mod P is isomorphic to the coordinate ring of this open Peterson variety associated to P. And in particular, in our case, I consider the parabolic to be a Borel subgroup, so we get a new presentation of the quantum cohomology ring, but we need to take localization at the quantum variable here. But if you consider Yp, then you don't need to take localization. And then there is another ring presentation of quantum cohomology ring coming from mirror symmetry. Since the flat variety are smooth and final, then mirror symmetry predicts that they should exist a superpotential, which is a family of holomorphic function defined on the dual space as check. And with the property that the quantum cohomology ring is isomorphic to the Jacobian ring of the superpotential. A simple example of this phenomenon is for P1, the one-dimensional projective space. Then the quantum cohomology is generated by one single element, sigma. And we consider the holomorphic function defined by x plus q over s defined on C star. Then the derivative of this function is given by 1 minus q over s squared. And you can check that we have two rings, then they are isomorphic by sending sigma to x. This is a ring presentation of quantum cohomology predicted by mirror symmetry. And we can even consider general flat variety. P1 is just a simple example, and the superpotential had been constructed by Li-Rietsch in 2008. And the definition looks like this. The domain lies in a Borel subgroup B minus, and you need to take the intersection with this thing. Here U plus is upper triangular nilpotent, and T is a torus, and W, Q, W naught are just Y group element. So for any element in the domain, you can have a decomposition into U1 and U2. U1, and then the function is defined by taking the sum of the matrix coefficient of both the diagonal of U1 and U2. And this function is well defined despite that you can have different choice of U1 and U2. What is remarkable about this function is that it recovers the Peterson variety. So Li-Rietsch proves that B minus is a critical point of FQ if and only if B minus inverse W naught B is a point in the open Peterson variety. So you consider this triangular diagram, and we have three commutative rings. In the bottom, you have quantum cohomology ring, and then Peterson construct a vertical isomorphism. He construct Yp circ and consider the coordinate ring, and then construct the superpotential FQ and consider the Jacobi ring. And these three rings are isomorphic to each other. And in our paper, I call this Peterson program. And in a joint paper with Li and Changzhen, we want to generalize the above triangular diagram to the case of smooth supervariety. And the domain of the superpotential we have is defined on B minus intercept U plus W bar. W bar is the permutation index, the supervariety. But we need to fix a decomposition of the element in the domain into U, V plus and B and U bar. I will not give much detail, but I will give a brief account of what the superpotential looks like. It's defined similarly, but with the fixed decomposition of the element in the domain. And the key point is actually lies in the positive rules I told you earlier. Remember that Rw consists of only simple rule if W equal to W naught Wp. This actually corresponds to the fact that in Lietsch superpotential, we only take matrix coefficient of both the diagonal of U1 and U2. But for general, we might have not just simple rules, we have higher rules. So for example, in type A, if the positive rules is alpha I, j in this set, then we need to take the matrix coefficient in the ij position of the matrix V plus with up to a sign. This is the definition of the superpotential for super varieties. And we also generalize the construction of Peterson variety for super varieties. And it again is a subvariety in G mod B. I only construct the open part because the open part of Peterson variety is the only thing you can recover from the superpotential. How do we define this? You consider the negative version of the rules I consider R minus W. And then for this set, you associate a vector space in the Lie algebra of G, U minus WP. And it is defined by the direct sum of G beta. Beta is the element in the set of negative roots, and G beta is the root space of beta. And I also fix a normalized vector zeta beta. And the torus is defined like this. And then I define the open Peterson variety YWP circ as like this. It lies in a supercells and has similar constraint as defined as in Peterson variety, such that the conjugate of U bar, if the conjugation of U bar on the principal nilpotent element F has certain pattern. And then the main result in the project of Li-Rietsch and Li, we proved that we have superpotential, we have open extended Peterson variety, and we find that the critical points of the superpotential we have can recover the open Peterson variety. So we have generalized the triangular to the case of super variety. So in the bottom, I will consider content cohomology of super variety and understand that super variety can be singular. And for singular super variety, we don't have content series yet. But when the super variety is smooth final, we can consider the conjecture that whether this extended Peterson variety give you a conjectural representation. Well, in fact, even for smooth super varieties, the computation of content cohomology of super variety is not widely studied yet. I think so. So this is some work related. Page studied the content supercalculus for odd symplectic Grassmannians for k equals to 2, and which is also, you can also consider it as a super variety. And 2019, Leonardo and Ryan gave an equivalent Monk-Chevalley formula equivalent version for the IG K2n plus 1. And this year, Chang Zheng and his collaborator compute the content cohomology of a Grassmannian GR2n and brought up along a subgrassmannian, and this you can consider it as a super variety in a two-step variety. And then in the remaining part, I will focus on the smooth super divisors indexed by W0 as n-1, and it is given by a single rank condition. E1 lies in Vn-1. And I can work out all the detail for this specific Y group element. And so first I write down the permutation matrix, and then I find the set of positive rules defined for this specific permutation. I can also get the negative version of the positive rules using the permutation matrix and the trick I told you before. And then we can apply the result of Li-Rietsch and Li and myself, and then we will get a conjectural representation of the quantum cohomology. And for this smooth superdivisor, it has a very nice description using the characteristic of the following matrix. So it looks very similar to the characteristic, very similar to the matrix for the full flat variety. And then the coefficient of the characteristic polynomial I denoted by hat E. So this is the conjectural presentation from the superpotential. And you, by simple computation on the determine, you can see that this hat E can also define using the ordinary contents symmetric elementary polynomials. And then the main result, we prove this conjectural ring presentation in the recent preprint. So we have quantum cohomology of this superdivisor isomorphic to this ring generator with x1 to xn and q1 to qn minus 1. And the relation are given by the coefficient of the characteristic polynomial of the matrix I gave you before. And then we also find that the superpolynomial, the quantum superpolynomial discovered by Fomin-Gelfand-Postnikov also give a representative of the superpolynomial in this superdivisor. Here I use the pullback of the superclass. And if you look at this matrix, if you set all the q to 0, no, you cannot set all the q to 0, sorry. Wait, yeah, you cannot. Because I need to take out a linear factor here, En. For the En, I need to take a linear factor here. But in the ring presentation, if you set all the q to 0, then you can recover the ordinary ring presentation of the superdivisors given by Gasser and Rayner, and also in Rayner, Wood, and Alice Young's papers. Moreover, we have a ring presentation. We have representative for the superclass, and then the question in supercalculus is the product of superclass. Well, in general, it must be difficult, but for some special superclass, you can multiply by a general superclass, and you can give the product. For example, if a superclass is indexed by a simple reflection, then such a formula is usually called a Monk or Chevalley formula, and we gave a Monk-Chevalley formula in the sense that for any simple reflection Sk, we give the product of the superclass index by Sk with any superclass index by U, and the formula is very explicit using the Broughat order or K Broughat order and quantum K Broughat order. So you can see that it looks very similar to the usual Monk-Chevalley formula for the flat varieties. Here is some examples. As you can see in the formula, that we sometimes have negative signs, so it's different from the full flat variety case. In the full flat variety, you always have non-negative integers. And here is an example. If you work out the combinatory the Broomhead order, and you can write down any example you want. And recall that we have a negative sign in the formula, but sometimes the negative sign cancel, just as the first example. But sometimes you cannot cancel the negative signs, just as the second examples. And then in the end, I can talk about a little bit about the proof, the idea of proof. For recall that we from the superpotential and the extended Peterson variety, we already have a conjectural ring presentation. And to prove the ring presentation, we compute the J function of the super variety using content lecture because we know the J function for the full flat varieties. And after we find the J function, you can find the content operators which is satisfied by the J function. And since the ring presentation is very similar, we also look at the content differential operators of the full flat variety and find the content differential operators that satisfied by the J. And this gives you the ring presentation. And then for the Monk-Chevalley formula, we just compute Gromov-Witten invariance and show that certain vanish. And in order to show the vanish of the Gromov-Witten invariance for degree dn-1 greater than 2, we use the curve neighborhood technique developed by Book and Leonardo. And then we have Monk-Chevalley formula proved geometrically. And then for the representative of superclass, we use the Monk-Chevalley formula to prove that the superclass satisfy a transistor equation. So you have an inductive relation for the superclass. And then you only need to prove that the content superpolynomials also satisfy this inductive equation. And this is observed by these 5 people in a recent preprint. And that's, I think, is the end of my presentation. Thank you again.
Thank you very much. Thank you very much for a very nice talk.